AET 105, Chapter 9, Network Theorems, Thevenin's Theorem. This theorem is probably one of the most interesting in that it permits the reduction of a complex network to a simpler form for analysis and design. In general, the theorem could be used to do the following. Analyze networks with sources that are not in series or parallel. Reduce the number of components required to establish the same characteristics at the output terminals. Investigate the effect of changing a particular component on the behavior of a network without having to analyze the entire network after each change. So Thevenin's theorem states the following. Any two-terminal DC network can be replaced by an equivalent circuit consisting solely of a voltage source and a series resistor. So this is the Thevenin equivalent circuit here. What you're trying to do is take a complex network, like they said, and break it down into simply a voltage source in series with a resistor. That's it. The resistor is called R Thevenin, and the voltage source is called E Thevenin. So here they show you an example. You have a load here between A and B. That's a variable load. We don't really worry about the load too much when we're doing this analysis. The part in the blue shaded area is the part that you want to reduce down to this Thevenin equivalent network. So you're going to take this complex network and break it down and boil it down to this simple network. So the first step is to remove the portion of the network where the Thevenin equivalent circuit is found. That would be the blue shaded area. Mark the terminals of the remaining two-terminal network as A and B. And then calculate R Thevenin by first setting all sources to 0. Voltage sources are replaced by short circuits. Current sources replaced by open circuits. And then find the resultant resistance between the two marked terminals. If the internal resistance of the voltage and or current sources is included in the original network, it must remain when the sources are all set to 0. And then E Thevenin, calculate E Thevenin by first returning all sources to their original position, finding the open circuit voltage between the marked terminals. This step is invariably the one that causes most confusion and errors. In all cases, keep in mind that it is the open circuit potential between the two terminals marked in step 2. And then conclusion, draw the Thevenin equivalent circuit, which is just a voltage source in series with a resistor, with the portion of the circuit previously removed in the blue shaded area replaced between the terminals of the equivalent circuit. This step is indicated by the replacement of the resistor RL, that's the load resistor, between the terminals of the Thevenin's equivalent circuit. So you can see in this example, you're identifying the part of the circuit that you want to reduce. In the blue shaded area, you label terminals A and B, and then you take out the load resistor because it's outside of the circuit that you're part of the circuit that you're concerned about. So you take it out. And then step 1 is to short the voltage source if there was a current source in here also, or you would have made it an open circuit. And then pretend like you have an ohm meter, a multimeter across these two terminals. So you're measuring the total resistance across these two. Now obviously with these two, R1 and R2 are in parallel. Okay, so you would figure out that equivalent resistance, which is going to be your R Thevenin. And then step 3 is to put the voltage source back in, and then E Thevenin across the terminals A and B is what your multimeter says that your multimeter voltage across from these two terminals is. So there's no current going through here because it's open, okay? So basically it's like sticking the ohm meter right here and right here like they have shown here. And this example would be a voltage divider. It's the voltage just across R2 as opposed to the entire circuit. So you guys know how to find that. And then what you do is once you found R Thevenin and E Thevenin, you put them back in with RL back in the circuit, and that's your Thevenin equivalent. So here they're doing another example. They have, forget about figure 9.31, we're on 9.32 now. We have a current source in parallel with the resistor, and they're both in series with R2, another resistor. You identify your Thevenin circuit, you put your terminals mark A and B. This is your load resistor right here. So what you do is take out the load resistor, and then first step, since this is a current source, you make it an open circuit. You find out the equivalent resistance across these two terminals, which is just, since this is open, you can disregard it, and it's just R1 plus R2. And then you put your source back in, and you can do a source conversion with these two. So to do a source conversion, E equals I times R, so it would be 12 times 4. That will be a 48 volt source. And this is going to be in series with a 4 volts resistor, or 4 ohm resistor, I'm sorry. And that's also in series with R2, which is a 2 ohm. So what they did was they added the 4 and the 2 together because they're in series after you do the conversion. And you get E Thevenin is 48 volts, R Thevenin is 6 ohms. So from the notes, Thevenin's theorem permits the reduction of complex networks to simpler form for analysis and design. The procedure: remove the portion of the network where Thevenin equivalent circuit is found. Mark the terminals of the two terminal remaining network A and B. Number 3, calculate R Thevenin by setting all sources to 0. E equals 0 is short circuit. I equals 0 is open circuit. And number 4, part 4 is with sources restored, calculate E Thevenin by calculating the overcurrent open circuit potential between the two terminals. And actually there's a step 5 in here, which is redraw with Thevenin equivalent circuit. Okay, so here is the substitution of again, the blue shaded area, which is a part of the circuit that you want to simplify to a Thevenin equivalent circuit. And then here's an example of how to do it. So problem 9 says find the Thevenin equivalent circuit for the network external to the resistor R, which is this resistor. So the first thing you do is you find R Thevenin. So you short out this E, and then this E becomes a short. So then R1 and R2 are in parallel, and they're both in series with R3. So you find R1 in parallel with R2, which is 6 in parallel with a 3, which ends up being 6 times 3 divided by 6 plus 3, which equals 2. Add it to the 4, you get 6 ohms. So that's how you find R Thevenin. E Thevenin is you put this back in the circuit. And remember, this is an open circuit here, okay? So you're measuring the voltage across this open circuit. Since no current is flowing through R3 because this is open, then the equivalent E Thevenin voltage ends up being the voltage across R2. To find the voltage across R2, you take E Thevenin equals R2 times your source voltage E divided by R1 plus R2. This is a voltage divider. So 3 times 18 divided by 3 plus 6 ends up equaling 6 volts. So your Thevenin equivalent circuit would look something like this. E Thevenin would be 6 volts, R Thevenin would be 6 ohms, and then you'd have this load over here, which they just called R. By the way, this symbol with a resistor with a line through an arrow through, that just means variable resistance, like a varistor or something you can adjust the resistance on. So then in part B, it says find the current through R when R is equal to 2, 30, and 100. So the current, if you make it into a circuit like this, the current going through it is going to be the source current from this source, from E Thevenin. So if this is 6 volts and R Thevenin is 6 ohms, then to find the current, you just take the Thevenin voltage divided by R Thevenin plus R, because it's a series circuit. So you get 6 over 6 plus 2 is 0.75 amps. And then if you keep substituting in for R, and this one you put in 30, you get 166 milliamps, 167. And then they just called them I1, I2, I3, but they're just talking about 3 different currents going through R. And then in the third example, we put in R equals 100 and get this answer, 56.6 milliamps.